Okay, so we'll go ahead and get started. The first half of today's lecture will dive into the weak acids, and those are the organic functional groups. So we're going to go through the table of what those pKa values are. Then we're going to look at the factors that affect acidity. So periodic trends, hybridization, resonance, and induction. Then we'll look at how do we match the pKa to the different bases. And then we're going to look at things that are not Bronsted-Lowry acids, but Lewis acids, where there's no proton transfer. And how do those acids react with organic molecules? And then about halfway through, we'll switch over to alkanes, where we'll start nomenclature. And then that will get us into this other subject of conformational analysis as we move forward. So at this point in the semester, we're really now looking to describe molecules in more depth based on these different concepts. So when we classify things according to methyl, methylene, methine, we'll also use other terms, primary, secondary, tertiary. And then we're going to get into what are the bond strengths. So our goal here is to be very rational about how we look at a starting material so that we can rationally predict where the reagents are going to act upon it and what the major products will be. So we left off the discussion about these strong acids, and when they're added to water, they always ionize to hydronium. So water is called a leveling solvent. So no matter what, you're always going to get H3O plus. But for the weaker acids, which are the functional groups, that's not always necessarily the case. And so we have to match the pKa of the functional group to an appropriate base, and then we need to consider what sort of solvent should we run the reaction in. So the complicating factor about all this is all of those things are organic molecules. The solvent is also an organic molecule, so we need for it to be inert. It can't react with our base, and it can't react with our starting material. So those things have to be aligned for a successful reaction. So the pKa scale, we'll draw it here, say most acidic. Let's say negative 15, then we have sort of 0, and then 50, least acidic. So the 0 in that scale is kind of the separation between strong and weak. And remember that it's a log scale. So we're reporting these basically whole number integers. But the difference between one pKa unit, since it's a log scale, is 10 to the nth power. So there's a massive difference between any one unit on the pKa scale. So from 0 to negative 15, those are strongly ionizing. Typically, they form hydronium. And then from 0 to 50, that's everything else. And so with all those functional groups, we have to consider what gets deprotonated and then what is the conjugate base that results. So one of the things we'll look at in comparing acid-base reactions to determine how the equilibrium shifts is the acid and the conjugate acid. So we're going to say delta pKa, where we compare those two values and then take the difference, but realize, say if the difference is 3 in pKa units, really it's 10 to the 3 or 1,000. And so we'll talk about how do we match acids and bases to affect the equilibrium. So the weak acids are all the organic functional groups that we've learned so far. And this table is arranged according to the pKa column. So remember that the smaller that number, the more acidic. So the first one listed here is carboxylic acid. And I've just given an example of that. Ethanoic or acetic acid. And the pK value is 4.75. Granted, you take your exams online and you can access resources and stuff, so you can look these tables up. But you want to have a general idea of where different functional groups lie. I'm not a big proponent of memorizing digits out to like 6 decimal places, so kind of just round everything to the nearest 5. So carboxylic acid generally has a pK of 5. And so the acidic proton is that one. And then you see in the conjugate base column, it's been deprotonated. And so that the name of that functional group is now a carboxylate. So you have your name, that's the functional groups you've learned, and then they slightly change as you form the negative species. I'll kind of run through a little detail or two for each of these, not too much, but so moving down, now we're up to about 10. And so notice this one, it's an amine salt. So the example I've given is protonated ammonia, so NH4, and that's plus. So this is, just to be clear, this is not your neutral amine, this is the salt. So it has that plus charge. When it gets deprotonated, it forms ammonia. And so that's a pK of 10. The other thing I want to point out, from the acid, that's neutral. The conjugate base is negative. This one, since we're starting with a positively charged species, the conjugate base is neutral. So pay attention to the charges and remember how you calculate them. So within that region, about 10, the next one is an aromatic alcohol, and the compound is called phenol. So it's a benzene ring with an alcohol. I'll try to squeeze it in up here. So it's OH. And then the alcohol group is bonded to a benzene ring. So the fact that that's aromatic separates it from the other alcohols that we'll see down below. So when we deprotonate that, we get phenoxide. So now this oxygen is O-, and then that's just the name of that base. So our next compound is water. So H2O, the pK is 14, that forms hydroxide, OH-. As we saw before, water is an interesting molecule. So here it's acting as an acid. So it's donating a proton, it's forming OH-. But water can also act as a base, because when you treat it with a stronger acid, that's what gets protonated to form hydronium. So you do have to have a general feel of strong versus weak, and if water is present, how is it acting? Is it going to act as an acid or a base? So as we progress down this column, notice the numbers are getting larger so that the acid strength is getting weaker. Now we're in sort of the general alcohol region, where the thing that's bonded to the OH is not an aromatic ring. So these are about 16. So, again, that's not a hard value of 16. It can fluctuate a little bit, and we'll talk about how it does that. So that H gets deprotonated, and this forms a negatively charged oxygen, so that's called ethoxide. So as we learn, the names of these reactive intermediates, the ending of the nomenclature, IDE, that typically means a negatively charged species. So we'll see like carbon, nitrogen, oxygen. When they form these species that are either plus charge or minus charge, they'll have a theme to what the name is, and you can infer how it's reacting. So far we have OH, a positive NH, OH, OH, OH. The next one is a ketone. So that molecule is propanone. This is also called acetone. So notice in there now, it's no longer an OH or an NH. There's only one unique set of hydrogen, that's CH, that belongs to methyl groups. So you have these two methyl groups. Those are the carbons bearing the hydrogens. There's no more heteroatom H bonds. If we classify those two carbons, they're sp3 hybridized. So we have sp3 H bond. Now when we look at that pK, it's about 20. So one of those CHs gets deprotonated. That means a carbon becomes negative, and that reactive intermediate is called an enolate. So IDE and ATE at the end generally mean negative for nomenclature. The next case is an ester. So let me draw that one out. So this one is an ester, ethyl ethanoate, or ethyl acetate is a more common name. So it's a little less acidic now. And when you look at this molecule, how many unique sets of hydrogen do you see? Three? So we have 3 unique sets. So 4 carbons, 3 unique sets of hydrogen, and that ratio is 3 to 3 to 2. So what I'm trying to get at in terms of, the uniqueness and now tying that into the functional groups. So those 3 sets, there's 1, 2, 3. all of those carbon atoms are sp3 hybridized. But these H's are the most acidic. So those 3 hydrogens relative to those 3 and those 2. These have a pKa of 25. And if we go back to acetone, see how it's methyl group and then carbonyl? The ester also has that, methyl and then carbonyl. So how do we explain the difference between those hydrogens being about 25? Then if we look at these other 2, which are sp3 hybridized carbons, they fall all the way down here. They look like alkanes. Their pK is about 50. So based on hybridization alone, we can't explain why there's such a difference in acidity. So 50 minus 25 is 25 on the pKa scale. If you translate that back from the log function, it's 10 to the 25. So these are way more acidic. What makes them more acidic? And we'll talk about that in the next couple slides. So the next one is alkyne, and the example given is ethyne. So for an alkyne, you have to have a terminal CH. And so we know that that carbon of the triple bond is now sp hybridized. So it must be a terminal alkyne where you have that relationship, CH. And those are about the same, 25. So when that H gets deprotonated, now you have a negatively charged carbon. That's called a carbanion.
You said it has to be a terminal alkyne?
Yep.
Okay, so if it is internal, then that's not going to be the case.
Correct. So notice the difference now. The prior 2 are called enolates. This one's just called a carbanion. And that's related to the functional group that's being deprotonated. We're going to skip ahead to pK 35 now and look at H2 hydrogen. So if we want to deprotonate an H from hydrogen, that generates H minus, which is called hydride. And as I said, the second entry was an amine salt. So that was positively charged nitrogen with at least one NH bond. Down here now is the neutral amine, so ammonia. Now it's just an NH bond. The nitrogen has its lone pair. When you deprotonate, you form this species. Now nitrogen has 2 lone pairs, so it has a negative charge. These things, for whatever reason, are called amides. But in your mind, if you can picture what an amide functional group is, it's not the same thing, right? So you'll have to recognize the context of how that name is being presented to you. But a negatively charged nitrogen, that's called an amide base. And then we finish off with our 2 remaining hydrocarbon functional groups, alkene, where the carbon is now sp2 hybridized. That pK is about 45. That forms a negative charge on an sp2 hybridized carbon. That's also called a carbanion. And alkanes are the weakest acids. So sp3 hybridized CH tops the scale. Those are essentially, one way to think about it, they're pretty inert. They're not reactive. We can still deprotonate them It just requires a really strong base to do that. And so we have these kind of heteroatom, OH, NH. Then we get into some alcohols, some sp3 hybridized carbon H acidity. That's more acidic than what we see for the inert ones, so we want to explain that. And then we have the different hybridizations of carbon. So sp, sp2, and sp3. So really what we're learning is not only how do we deprotonate these functional groups, but then how do we use them in reactions. And then the other thing is, for some of these, we're going to deprotonate them to make these bases. And then we're going to use those bases in a subsequent second acid-base reaction before we do the main thing that we want. Any questions? Using this chart, most likely you are not going to find the exact functional group situation you're interested in. Really, you're just looking for sort of carbon hybridization, and then where does it fall within this? So any sort of alkane CH is about 50. You're never going to find like the exact sort of CH in your molecule that you're after. So we'll look at some of the factors affecting acidity, and the first one's the periodic trend. So in our first row here, we're just going to move across that period 2 and look at those main elements: carbon, nitrogen, oxygen, and fluorine. So I've listed the electronegativity value. That's the Pauling number there. And we know that that increases towards fluorine, moving across and then moving up the group. The acid that I'm showing is just, that element with the maximum number of hydrogens. So we know carbon can form 4 valencies, so we're going to use methane, ammonia, water, and then HF. Below it is the pKa value from that chart. So so alkane 50, ammonia 38, water, got a boo-boo here, that should be 14. And then HF is 3.2. So remember, the larger that number, the weaker the acid. So whatever H is bonded to that element as you move towards fluorine, that is increasing the acidity of that XH bond. And we can partially attribute that to the electronegativity. So if you take your acid, you deprotonate it, that's your conjugate base. So since all of these were neutral, the base that we form is going to bear a negative charge. So acidity and basicity are opposite trends. You have a weak acid. When you form CH3 minus, that is a very strong base. HF in the series is a strong acid, so F minus is a weak base. So what we want to do is, when we're classifying the unique sets of hydrogen, what functional group do they belong to, and then what is the associated pKa? Meaning how or what base should we choose to deprotonate that? So the other thing, this trend is showing you sort of moving horizontally. Typically, when you're moving down a group, so like as we saw with the halogens, acidity will increase due to the atomic radii increasing and then polarizability. Any questions? You might have to draw some things in. I think I didn't get a full copy paste here. I think your H's are missing on the slide, and then this front arrow here. So the next thing we're going to talk about is the resonance effect. So remember, in general, resonance is a stabilizing factor. So anytime you can, delocalize a charge around, that stabilizes it. And the things I want to point out on this slide, we're starting with a carboxylic acid. So it has 2 carbons, ethanoic acid. And then below that is ethanol, so a 2-carbon alcohol. They both have OH and OH. If we assign pKa values, these things shown in red here, to each unique set of hydrogens. So ethanoic acid has 2 sets, this H and then that methyl. We can go to the table, see what the pKa value is for those functional groups. So a carboxylic acid is 5. This type of sp3 hybridized carbon next to a carbonyl and an ester is, or an acid is 20. Now, compare, put your eye here and kind of just go straight down for each carbon as you move away from that alcohol. So there's no H's there, so we can't assign a pKa. But we have 2 H's there. Those carbons are sp3 hybridized, so they're alkanes. We would say they're 50. That carbon and that carbon are both sp3 hybridized, but look at the difference. That's 20 and that's 50. So clearly this carbonyl group being present is increasing the acidity of those hydrogens quite a bit. So that's one thing you'll want to be able to do. Identify those numbers for every unique set. In terms of the reaction shown, we have OH of an acid, OH of an alcohol. Those are both being treated with sodium hydroxide. So the arrow pushing shows how the electrons are moving. Sodium hydroxide, that means the conjugate acid on both sides or both reactions is the same. It's water. The pKa of that's 14. So 14 and 14. Now here is the conjugate bases. So the carboxylate and the alkoxide. Notice the difference in arrows here. When you see this one-way arrow, that means the reaction is favoring this completely. When you have this back and forth, remember, equilibrium does not mean 50% that and 50% that. It's coming up to some concentration of each. And the reason that we use this instead of that, we have to compare these numbers. That conjugate acid and then that acid. So that's the delta pKa. So we'll use the absolute value of that. So for the top one, it's 9. And then the bottom one, it's 2. So a general kind of rule of thumb, if that value is greater than 5, now remember that that's the pKa difference, but really that's 10 to the 5. So we would say the reaction's irreversible, meaning you draw the arrow like that. When it's less than 5, then you have to draw these arrows. So practically speaking, why is this important? Why is it an issue? When you run a reaction, you want it to go to this stuff. So you would take your acid, your base, then it's forming this in water. When you have that smaller difference, the issue now is instead of having 2 things in the reaction, you have 4. Your alcohol, your base, the alkoxide, and the conjugate acid are all still present in solution. So you don't want that if you're going to do something productive in the reaction, because now you have so many ways that these things can sprout off and form byproducts that you would end up with a mess. So by controlling the nature of the base that you use, you can affect that equilibrium to make it irreversible. And so now this is the main sort of reactant moving forward, rather than having a choice of 4 different things being reactive. So the take-home message, when you draw your acid-base reactions, identify all the pKa's. The 2 main ones are your acid and then your conjugate acid. So this is pretty much just a summary of that. Maybe another way, just so I don't duplicate the same slide here. So as shown originally, they're kind of 2 separate reactions. But what if you put both of those functional groups into one molecule? So now you have an acid and an alcohol, and you treat it with 1 equivalent of sodium hydroxide. What reacts first? So the base is always going to go after the strongest acid. And so in a polyfunctional molecule, something that has more than 1 acidic functional group, the base always has to go at the most acidic thing. So it can't go there first because that is not favored. What are the consequences of that? It allows you to react specifically on this oxygen. So we can deprotonate that, do a reaction there. Then if we wanted to do another sequence, this OH would be the next acidic one. So that's how you start sequencing things to make complex molecules. So a way that you could think about foreseeing this on an exam, it could be presented to you in two ways. Given these 4 different molecules, which one's the most acidic? Or given this one molecule, which hydrogen of the polyfunctionality it has is the most acidic? Or what base would be appropriate to react with whatever functional group? So in my haste, I realized we forgot to practice. Sorry about that. Resonance. Let me actually explain that now. OH and acid versus OH and alcohol. Why are these two so different if it's just OH? If we look at the carboxylate, we can delocalize the negative charge that's on oxygen to the other oxygen. So for the carboxylate, there's 2 resonance forms. Those are hybrids. And essentially what it's telling you is the negative charge is delocalized over both. That helps stabilize it. In the alkoxide case, that negative charge is stuck on that oxygen. It has nowhere to go. So we can use structural features of this starting acid, but then we can also consider these things of the conjugate base that help stabilize it. So yeah.
So the resonance is a way to indicate that it's going to be an irreversible reaction? Or it's just more likely to be irreversible?
Yeah, again, I don't want to get too much into the nuance, but that arrow that you draw, again, that is dependent on what base you're starting with. Because when that base deprotonates to form the conjugate acid, you're really comparing those numbers, that one and then your starting acid, when you do that delta pKa. So again, resonance that's the delocalization of electrons, either through a 3 or a 2 atom system. Again, resonance, you're not moving the atoms themselves around, so you can't do that. So try to keep these names straight, because we'll see other situations that sort of look like resonance, but they're not really. So the next one was the inductive effect. So tug of war. So in this top case, I'm highlighting in blue the elements for a carboxylic acid. So all of those red dot carbons are sp3 hybridized, they're the same. But when you look at what's bonded to them, here you have 3 fluorines, and then over here you have 3 H's. So the way to explain why this becomes more acidic as you add those heteroatoms is that through bond or tug of war effect, that is induction. So I'll try it in green here. So because those fluorines are electronegative, they're basically just pulling through that sigma bond network. And as they tug through that, one way to think about it is this OH bond is getting weaker. So if we imagine that H kind of stationary, the fluorines are pulling, and that's pulling the oxygen away from the H. In the series below, let's see if I can remember some stuff here. One nomenclature to identify carbons on a chain with a carbonyl. The carbon next door is called the alpha carbon. And then as you move out, you just use the Greek alphabet. So here we have the heteroatom bonded to the alpha carbon. The next one, it's the beta, gamma, and then delta. So as that heteroatom moves farther and farther away, its effect through induction decreases. So if the heteroatoms are right on the alpha, those are going to be the most acidic. And then by the time it gets past the gamma or the delta, this pKa value is essentially just kind of the same, about 5. Questions? So the next trend is we're going to look at carbon hybridization. So now these are your CH bonds with sp3, sp2, and sp. So the trend here is sp3, CH bonds. Again, those are specifically for terminal alkynes. It has to be that situation. Those are about 25. When you go up to alkenes with sp2 hybridized carbon, so alkenes are aromatic rings. There's about 45, and then your average sp3 alkane is 50. So in this molecule gifratoxin, if you were to assign, all the unique sets of H, there'd be quite a bit. Of all of the hydrogens in there, this OH would be the most acidic because it's an alcohol. It would have a pK of about 16. But then if we started to rank the other hydrogens, and we look across, the total backbone, now they're all CHs. So of that, when you rank them according to alkyne, alkene, and alkane, the alkyne is going to be the most acidic. So if you deprotonate that and then you treat it with a strong enough base, the next thing that's going to go is this one. So that's an sp hybridized carbon H bond. Then we have an alkene, so that's sp2. This last HA here, I've just indicated one, it's sp3 hybridized carbon, but if you look at all of the carbons that are sp3 hybridized, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what does that tell you? If you wanted to run a reaction where you modified this structure right there, it would be very difficult because you have 14 other places that are competing for it. So as we learn reactions and design syntheses, you have to consider, how can I control all this stuff? That's basically what organic chemistry is about. I want to take crude oil of some alkane and I want to make it into something valuable that I can sell, but I need to do it in a very rational way so that I only produce one thing and not 20 things. So the reason for this, this trend is due to this percent S character of the hybrid orbital. And again, that comes from, there's two atomic orbitals, S and P. The percent S character is 1/2. So that gets you your 50. And because the S orbital is spherical, it's closer to the nucleus, it's better able to stabilize the resultant negative charge. So the thing I want to move into now is the reason why when you have sp3 hybridized carbon H bonds, why can there be such a big difference in acidity based on what functional group it's a part of? And to demonstrate that, we'll look at diethyl ether. So this molecule has two unique sets of hydrogen in a ratio of 6:4. And so you have 2 and 2, that's your 4, 3 and 3, that's your 6. I've just shown the pKa values for all of those different groups. When you look at the carbon hybridization for each, it's sp3. So that's going to categorize them as alkanes, so the pKa's are 50. So the ester, ethyl acetate, that has 3 unique sets of hydrogen in a ratio of 3:3:2. Notice this group OCH2CH3 is kind of the same, so those values don't change. But this carbon in red, we've swapped it out now for a carbonyl, so that hybridization changed. Now look at the effect on this carbon from 50 to 25. The reason that these become more acidic, even though they're still the same hybridization of carbon, when you deprotonate that, the negative charge can be delocalized through resonance onto that oxygen. So I'm going to cheap out and just say B minus for base. So the base can abstract. The electrons go on the alpha carbon. Now that lone pair will be delocalized. So we form a carbon-carbon double bond. We break the carbonyl. Our resonance form. Now puts that negative charge on oxygen. So the resonance argument is what can explain the difference in that acidity. So I know I'm probably going to jam some stuff up here, but if you decide to continue on with the journey into organic 2, we're going to talk more about carbon-carbon bond formation with this concept. So I've drawn another ester here. I've identified the alpha carbon, the beta, and the gamma. Under these conditions, you are only concerned with the alpha carbon. The beta and the gamma behave as alkane acidity, so they're both 50. So of this molecule, when you treat it with a base, you are selecting a CH bond here only. If you had a strong enough base, you could never go here first. The pKa's don't allow it. So the alpha carbon in organic chemistry is special. I would say the reason that we as humans and scientists study it is because in biological systems, that's how a lot of carbon-carbon bonds are made. So in organic 2, we'll talk a little bit about biomolecules, but say when you're eating, they say don't eat foods with high cholesterol in them. So you're getting the cholesterol from some external source, but your body also makes cholesterol. And it makes it from 2 carbon units that grow, and then they cyclize into the steroid. And the strategy of that is always a 2 carbon unit where the alpha carbon is the reactive one. So now that we know the functional groups, the different trends that affect acidity, what are some of the common bases? I want to draw a line here. So you see these bases, the first couple here. So sodium ethanoate. That's the conjugate base of a carboxylic acid. So now you see the acid form. And I've taken that and related it to the pKa table. So we use those acids to form bases. And as we'll see on the next slide, you have to appropriately choose a solvent that is compatible with that acid-base mixture. So these first couple are derived, these first three are derived from OH functional groups, so acid, water, or alcohols. So your starting acids, we use them as bases. Sodium amide is derived from ammonia, so this starting value is a weak acid. So sodium amide is a strong base. And the reason I drew that line is because when you look at the base in the acid, they're typically, not only the solvent, but the acid or the base. When you get up to pKa's that are weakly acidic, meaning these bases are strong, like really strong, then you have to choose an appropriate solvent to run the reaction in where this base will not deprotonate the solvent. We call that quenching. So lithium diisopropyl amide, or LDA, that's a really strong nitrogen base. A really strong carbon base is derived from butane called butyl lithium. So these things come in glass bottles, and you have to transfer them with a syringe because they will react with air to form little torches, and if you're not careful, other things can happen. So these are really strong. And the other thing to notice, so we have sodium or lithium. Those are the most common sort of spectator ions for these. You're either going to use like a group 1 or a group 2 cation to balance the charge. And practically speaking, what you use, if it's lithium, sodium, potassium, or magnesium, relates to the solubility in the solvent that you're using. So I can't stress this enough because when we start learning reactions, you have starting materials that you want to transform into products, and the reagents are what make that happen. But remember, all these things are different physical states, so they have to be in solution for a reaction to occur. And so the solution is the solvent. And we need the solvent to be inert to the reaction conditions. It's just there to solubilize stuff so everything's in solution. And then we can also use it as a heat source or a heat sink. And when we start talking about thermodynamics, if a reaction's sluggish, what can we do? We can heat it, raise the temperature, or if the reaction itself produces heat, the solvent can soak it up. So that the yellow, there's yellow and this neon blue looking thing, turquoise here. The yellow ones are called protic solvents. Protic means you have OH or NH. The blue ones are aprotic. That means there's no OH or NH that's acidic. So notice how they're matched. You know, these things where you're forming O-, those come from those acids or alcohols. Those are protic solvents. And then when you need to bring out like the heavy hitters, the really strong bases, you have to use these aprotic solvents that are inert. So in general, these are usually alkanes or ethers because they do not have acidic hydrogens. Any questions? So this table is basically a summary of all that. Here are your different functional groups. Here are those different bases. Here's the formula of those bases. And now this column is the pKa of the conjugate acid of these things. And so the stoplight, green, yellow, red, is basically telling you what base is appropriate to react with that functional group. So for a carboxylic acid functional group, you can use pretty much any of these bases. When you start getting into the yellow, you'll see that when you match the pK of the functional group to that from the base that you're using, they're not terribly appropriate because they're going to be reversible. So the stuff that's in green, those are your irreversible reactions. And the stuff that's in red, those bases are not strong enough to deprotonate those groups. It's like a buffet, right? A little bit of that, a little bit of that, a little bit of that, that. By the time you're at the end of the line, your plate's that tall, you realize you're not that hungry. So let's see if we can make sense of this. We have that ketone. It has one unique set of hydrogens. So CH3, I've just shown one of those 6. The pK is 20. If we want to form the enolate in an irreversible manner, what base should we use? If we want that equilibrium, what base should we use? Any guesses? So A is the correct answer. So how are we arriving at that? If that's your base, which is deprotonating that, draw the conjugate acid for each. So this is called LDA. So its conjugate acid is diisopropylamine. That pK was about 45 or something. For potassium tert butoxide, the conjugate acid was that alcohol. That was about 16. So you look at your starting acid, the pK of the conjugate acid, and you do the difference. So here you have a difference of 25. So 25 versus 4, and if that difference is greater than 5, we would say it's irreversible. So these other ones, when you compare, hydrogen versus water, water, or LDA versus butyl lithium, these are both, D is going to be irreversible for both. C is going to be reversible. And then these, I think, are flipped around. So you have a strong base here and a weak base there. So the main thing is looking at the pK of the conjugate acid. Questions? So I probably told a fib. We're not going to get to the nomenclature today, but we'll finish off on these next two slides here, where we're going to look at acidity where a proton is not transferred. And so this falls into the Lewis definition, where we're looking at electron movement only. So maybe one of the frustrating things about this course is we're going to introduce this topic now, but not going to focus on it too much. We'll revisit it at later points, but we still need to understand how this falls in to those three definitions. So Lewis acids are reagents that we use to help activate functional groups. And so I've shown two here, boron trifluoride and aluminum trichloride. So there's our cheap periodic table. And we focused on the bonding patterns of CNOF. If we say carbon is group 4, boron would be group 3. And so what do you notice about boron and aluminum? As compared to how you would draw a Lewis octet, they're electron deficient. They don't show 8 electrons. They only show 6. So 2, 4, 6. It still has the possibility of forming the 4 bonds to achieve an octet. And the way it can do that is it has an empty p orbital. So that p orbital is unfilled. That makes it a Lewis acid, because a Lewis acid can accept a pair of electrons. A Lewis base donates electrons. So notice in those reagents, there's no hydrogens, right? So we're not talking about a proton transfer, we're talking about electron movement. So how do these things engage with organic functional groups? So let's consider BF3 and then this aldehyde. not going to let me do that. I want to redraw that. So I'm going to draw it with the form where I'm showing that p orbital. So if that's a Lewis acid where we have an empty p orbital, the butanal must be a Lewis base. And so where are the electrons coming from? What? So just one thing, we're not transferring a hydrogen. We need some electrons. Does anything in the butanal have electrons? The double bond does, but what else? So the oxygen has 2 lone pairs. Lone pairs will move before electrons in a pi bond will. So those lone pairs will attack that p orbital. When it does that, notice I haven't drawn a second arrow. We are making a bond from oxygen to boron, but we are not breaking a boron-fluorine bond. So that's what we've formed. So we could call that a Lewis acid-base complex. But now the oxygen, neither the oxygen nor the boron are in their normal pattern. So they should have some charges. What gets what? So oxygen gets positive, and then boron gets negative. So we started neutral, we added charges, they balance out to neutral. And I said these things react with functional groups to activate them. We could draw a resonance form where the pi bond now puts the electrons back on oxygen, so it's neutral. So the plus charge now goes to carbon. And so what we've done is we've activated the carbonyl group. And so what does that tell us? That carbon is now electron deficient. So something with electrons can attack it. And we can make a bond to that carbon. So the Bronsted-Lowry versus the Lewis acid react in different ways, and you'll want to know, your acid base where protons are moving, but also how Lewis acids engage with different functional groups. So I think with that was the last acidity slide, and then Wednesday we'll start with alkanes and nomenclature.